The first Tacoma Narrows Bridge opened in 1940. It was a suspension bridge in the U.S. state of Washington that spanned across the Tacoma Narrow Strait of Puget Sound between Tacoma and Kitsap Peninsula. At the time, it was the third longest bridge in the world. Clark Elridge completed the original design for the State Toll Bridge Authority, but not long after, New York Bridge engineer Leon Musser provided federal authorities with an alternative design of a suspension bridge to provide a more elegant design and at a reduced cost. Subsequently, $6.4 million of funding was provided to the State Toll Bridge Authority, which was less than the $11 million originally required for Clark's design. Along with the funding, federal authorities required the Toll Bridge Authority to hire Mosef as a consultant and include the proposed changes. The state's experts called Mosef's plan fundamentally unsound. The design made the Narrows Bridge lighter and narrower than any other bridge ever built. They said it was in the interest of economy and cheapness that these changes were made. Construction began in 1938, and even before completion it was given the nickname Galloping Gertie early on due to the wave-like motion of the bridge. However, on the morning of November 7, 1940, something changed. The bridge deck began to twist rather than bounce, and this steadily increased throughout the morning before ultimate failure occurred.
Hi, I'm Tom. I'm going to talk about the formal inquiry and the cause of collapse. The Federal Works Administration, or FWA, appointed a three-member panel of top-ranking engineers, Othmar Ammann, Dr. Theodore von Karman, and Glenn Woodruff, to conduct a formal inquiry into the collapse of the Tacoma Narrows Bridge. Their findings were that the failure resulted from excessive oscillations caused by the wind's action, and that these oscillations were made possible by the extraordinary degree of flexibility of the bridge. The vertical oscillations were probably caused by the turbulent nature of the wind, and that their amplitudes may have been influenced by the aerodynamic characteristics of the structure. Their findings concluded that it is reasonably certain that the first failure was the slipping of a cable band on the north side to which the center ties were connected. This slipping probably initiated the torsional oscillations that we saw in the video. The torsional oscillations is that twisting motion. It was reported that the suspension type bridge was the best and most economical type of bridge that could have been selected for the Tacoma Strait at the time, and that the quality of materials and workmanship were of high order and not the primary cause of failure. The exact cause of collapse is still debated today by many engineers, which really just goes to show how phenomenal this disaster was. It really opened the eyes of the engineering community to the impacts of wind and aerodynamics on suspension bridges. The fundamental weakness of the Tacoma Narrows Bridge was its extreme flexibility. It had very little resistance to vertical and torsional movement because it had such a large depth to width ratio, 1:72. Its long, narrow and shallow stiffening girder made the structure extremely flexible. The first vertical oscillations were noted during the build process. This movement was often witnessed even on mildly windy days. Really, this should have been a big red flag to engineers and constructors of the Tacoma Narrows Bridge, just that something was wrong. On the morning of November 7th, 1940, the bridge was experiencing strong winds of up to 74 kilometers an hour. The previously mentioned vertical oscillation of the bridge deck resumed. Shortly after 10 a.m., a critical event occurred. The cable band on the north cable slipped. This allowed the cable to separate into two unequal segments that contributed to the change from vertical to torsional movement of the bridge deck. In this image, we can clearly see the twisting movement of the bridge. Also contributing to the torsional motion of the bridge deck was what is known as vortex shedding. Vortex shedding is when wind hits a blunt object, and this flow separation creates alternating low pressure vortices on the backside of the object. This simulation shows how the pressure alternates and pushes and pulls the object from side to side. The wind was forced to separate as it hit the side of the deck, which on the Tacoma Narrows Bridge was a solid plate girder. More common bridge design now uses design that allows wind to flow through the structure of the bridge to avoid this flow separation. So as we can see in this diagram here, more common bridge design uses the drawing on the left-hand side, where you can see that wind could pass through that structure. Whereas the Tacoma bridge had a solid plate girder, so the wind had to separate, had to go either above or below. This created that vortex shedding. This diagram gives us a little bit of information on how these low pressure vortices actually impacted the bridge. So if the swirls you take as the low pressure zones, you can see how the bridge wants to naturally move into those zones. So if there's a low pressure on the top left and the bottom right, it's twisting it. So what happened is that it wanted to move back into its natural position of being flat. And as it did that, its momentum actually took it past and started twisting it in the other direction, at which point the wind could have a bigger impact on it and create more vortexes, so the twisting motion just kept happening. Now, the external force of the wind was not enough to cause the extreme twisting motion that caused the bridge to collapse on its own. The twisting movement of the deck went into what is known as aeroelastic flutter. The flutter is a harmonic vibration pattern. So the vortex and the deck's twisting motion became synchronized. So the bridge's twisting motion became essentially self-generating. At this point, the bridge cannot naturally lessen the torsional movement. The torsional motion began small and is just slowly building and building on its own energy, getting bigger and bigger. Once the torsional motion of the bridge became self-generating, progressive failure was unstoppable. Eventually, this torsional oscillation caused too much stress and the bridge collapsed. The main cause of collapse essentially comes down to the design of the bridge. The effect of wind on suspension bridges at this time in our history was relatively unknown. And in this era, design was based around gravity and how a bridge could be designed to hold the weight of the structure and those traveling on it. Secondary to that was how to do it economically, at the least cost to the taxpayer. Leon Moisseff's design met all the recommendations and was therefore chosen over Clark Eldridge's original design. The wind effect on the suspension bridge of this length was considered, but vastly underestimated, purely because we didn't know enough. I'll now pass you back to Jamie, who will discuss suggestions and recommendations. Thanks.
Thanks, Tom. Now, as I mentioned earlier, bridge engineers noticed during the construction phase that the bounce or wave-like motion was a cause of concern. To combat this, they installed hydraulic jacks between the tower and the deck to act as shock absorbers. But the devices made no noticeable improvement. It's understood that they were actually damaged during the sandblasting phase of the bridge. Not long after, Professor Bert Farquharson was contracted by the Toll Bridge Authority to create a wind tunnel study and recommend a remedy. He built a scale model and inserted it into a wind tunnel to try and identify a solution. His first solution that was done was he installed cables between the plate girder and the concrete block on the shore, as shown in the picture attached. But unfortunately, this didn't have an effect on the middle part of the bridge, which still continued to bounce. His final report was only submitted 5 days before the collapse, and unfortunately, they did not get to install his other mentioned options of repair. One was a curved outrigger on the side of the girder to deflect the wind flow and reduce that low pressure vortice. The other option was to cut holes in the side of the girder to reduce that pressure differential and the low pressure vortice. Just days before it, the Toll Bridge Authority approved the curved outriggers to be installed, and they had been planned to be put in within 1 month of the confirmed date. Unfortunately, a couple of days later, the bridge collapsed. The formal inquiry, as discussed by Tom, provided some recommendations and solutions to what went wrong and how it could be resolved. Unfortunately, the bridge was not repairable. However, some of the parts, including the cable anchorage, tower pedestal, and most of the remaining substructure, was able to be reused. The tower that supported the main deck and cables was not able to be reused. It was also noted that had there been a model done and wind tunnel testing conducted, that these issues may have been picked up. As such, from that point onwards, everyone was encouraged to ensure that aerodynamics and wind tunnel testing was included in any future design of any bridge. Engineers also noted that if an open and stiff truss similar to Clark's design was used, it was unlikely that the bridge would have failed. It would have allowed the wind to flow under the bridge rather than smashing into the girder and deflecting, creating that low pressure vortice. It was also advised that open sections, as per the picture, would have also helped reduce the movement. It would have helped the pressure differential and allow the wind to flow freely between each section of the bridge. The Tacoma bridge failure provided us many lessons that we have been able to input in today's bridges. Firstly, safety was the #1 concern and far more important than design. Second, any risk can increase when cost cutting can occur, and this should be looked at closely to ensure that the safety has not been compromised. Theoretical knowledge needs to be backed up by either past experience or testing. This includes modelling and simulation, which is all done today via CAD, via physical. There are many different ways of us conducting our testing and simulation. The last thing is, engineering disasters can have a positive outcome. Yes, it cost a lot of money. Yes, we did lose a dog. But we are lucky to say that there were no lives lost, and it's really been able to put us in a really good stead for future generations to build safe bridges for all. Thank you.